Hello everyone, this is Dr. Webb. In the last couple of videos we've been talking about permutations, and in the last video we specifically were looking at the cycle structure of permutations, and we found out that if you know what the cycles of a permutation are, what all of them are, then it's actually pretty easy to figure out what the order of the element is and lots of other nice information about it. In this video, we're going to be focusing in on what information we can get out of a permutation if we know how it breaks down into two cycles. So let's run back through some definitions just to refresh ourselves. So remember that a permutation is a function from a set to itself that is both one-to-one and onto. In general, we're thinking about permutations on finite sets. And so if a set has n elements, all the permutations on that set is what's called the symmetric group, and it's denoted Sn. And if we have some permutation in Sn, so really this is a permutation on a finite set, then we can break it down into a product of disjoint cycles. So as I said before, we're going to specifically focus on two cycles in this video. So what's a two cycle? Well, two cycle, it's just a cycle with just two elements. So these are often called transpositions because what a two cycle does is it just swaps A and B. It just maps A to B and B to A and doesn't touch any other element. So this single two cycle, it just swaps A and B and leaves everything else alone. Now, any two cycle has order 2. If you apply it to itself, if you swap A to B and then do it again, B goes back to A, everything goes back to how it started, and so that's the identity. And also the order in which we write it doesn't matter. So the two cycle AB is the same as the two cycle BA. They're both just saying swap A and B. Okay, so our first lemma is that if we have a K-cycle, well, then this K-cycle can be represented as a product of two cycles. And the proof of this is really in this line. So if we have a K-cycle on the left, and the claim is that this product of two cycles on the right is equal to it. And so let's just do some double checking on this. So one thing in particular, let's call this element right here sigma. Let's call it sigma prime to differentiate from our original sigma. And we want to claim that sigma prime is equal to sigma. So first, if I plug AK into sigma prime, or apply sigma prime just to AK, well, going through here, AK doesn't appear until we get to the very last one. And in that one, AK gets swapped with A1. So AK is sent to A1 just the same as what happens in sigma. AK is the last entry there. Okay. Now I want to think about what happens to sigma prime of AI where I is strictly less than K. Well, if we go through and think about what's happening in these cycles, eventually the pattern here is that we would have A1 AI in here, and then A1 AI plus 1, and then nothing before it and nothing after it would have either, nothing before it or nothing after it have either AI or AI plus 1. These are the only two places where they appear. And so if we do apply that all to AI, AI is going to skip over all of them until it gets to A1 AI. And so then A1 AI, let's do a little side calculation here. A1 AI applied to AI is going to give us A1. But then A1 then is going to go into A1 AI plus 1. And so A1 applied to A1 AI plus 1 is going to give us AI plus 1, and then AI plus 1 doesn't appear anywhere else down the line. So sigma prime of AI is going to give us AI plus 1. Okay, and this really works for all I going, well, all the way down. Let's do this starting at 2. And then the last but not least, if we plug A1, if we apply A1 onto here, A1 gets sent to A2, and A2 doesn't appear again. And so sigma prime of A1 is equal to A2. And so checking through here, this every AI is getting sent to the next higher index, except for AK, which is getting sent to A1. And so this is exactly the same thing that sigma is doing. And so if they're sending all the elements to the same place, then they must be the same permutation. And that completes the proof. Now, one thing I want to note, this representation of the K-cycle as a product of 2 cycles is not unique. And so I think another one we could do this is we could have it start a K minus 1, a K, and then a K minus 2 to a K minus 1, all the way down to A1, A2. This one would be A2, A3. And so my claim is that this is another representation of our original K-cycle as 2 cycles. And you can kind of check and go through. If you plug in AK minus 1, AK minus 1 is going to get sent to AK, and then AK doesn't appear anymore. So you're done. If you plug in, say, A1, A1 doesn't appear till the very end, and then gets sent to A2. The interesting thing is what happens to AK. So AK gets sent to AK minus 1, and then that gets sent in the next one to AK minus 2, and it keeps bouncing back all the way. You get A3, and then A3 gets sent to A2, and then finally A2 gets sent to A1. So AK in this one gets bounced one by one all the way back to the end. So the representation of a K-cycle as 2 cycles can be done many different ways, and this is just 2 examples of it. So a direct result of this lemma, and we'll call it a theorem, is that once we can break down a K-cycle into a product of 2 cycles, that means that we can break down any permutation into a product of 2 cycles, because any permutation is just made up of a product of cycles. Now, the one thing to note is that we no longer have once we get things down into 2 cycles, we're no longer getting disjointness in general. In general, when you break it down into 2 cycles, you can see in this one, A1 is popping up all over the place. So these are not commuting with each other. The order in which these 2 cycles are in are very important. Okay, so this is the main theorem for this video. And it's a little bit of a technical theorem, but it's very important, as we'll see. And so the idea is that if we take the identity permutation and we're able to represent it as a product of 2 cycles, so these 2 cycles in some way cancel themselves all the way out back down to the identity, then the number of 2 cycles involved has to be even. And most of the work for proving this theorem is going to be done in proving this lemma. And so the lemma says is that any time that we have epsilon represented as a product of R2 cycles, then we then can cancel in some way cancel 2 of those 2 cycles out and get it down to R minus 2 cycles. Okay, and so anytime we have it as a product of R2 cycles, then we are able to represent it using exactly 2 less 2 cycles. So this is a bit of a technical lemma, but this really is doing all the heavy lifting for pretty much all the theorems we have left in the video. Okay, so let's start off. We have epsilon represented as r different 2 cycles. Now, as we go through this list from beta 1 down to beta r, I want k to be maximal, so k to be the largest index, such that in these 2 cycles, one of the entries, at least one of the entries of bk, is less than or equal to both of the entries of bk minus 1, right? And so I'm thinking about something like something like this instance, where this is bk, beta k, this is beta k minus 1. And so if you notice here, this 5 is less than either 7 or 9. And we don't need less than, we need less than or equal to. So it would be okay even for, instead of having a 7 here, having that be a 5 as well. This would still hold true. This is, so we're looking for the largest index k where this happens compared to the one next to it. Okay? And so then this is what we're going to do. Okay. Well, so then looking at those 2 entries, there's only 4 possible forms in which they could do. So the first is that beta k minus 1 and beta k are actually the same. So they are AB, AB. Second one is like the one we saw before, where this is something like 5, 9, 5, 8. 5 appears in both of them. The next one is that they share one, but it's not the smallest one. And so this would be something like 7, 9, 5, 7, where they share 7, but 5 still is my smallest one. And then the last one is that they're completely disjoint. And so the one on the right has the smallest term, so something like 5, 8, and the one on the left has something like 7, 9. So 5 is still the smallest one, and they don't share anything in common. Okay, so let's copy those possibilities down. And then looking at these, if we get in the first case where the 2 beta k minus 1 and beta k are exactly the same, then we're done, because these 2 cancel themselves off, right? Any 2 cycle has order 2, so if you have 2 of them in a row, they cancel themselves off. We now have 2 less 2 cycles in our representation. Okay, so then all the work has to be done with what happens in these other 3 cases. So if we're in any of these other 3 cases, this is what we're going to do. Well, for each of these cases, we're going to, whichever one we start off with, we're going to use an equivalent product. And so you can go through and double check that each of these identities is true. And the important thing is that in each of these identities, now A is only appearing in the leftmost, in sort of where beta k minus 1 was, and is no longer appearing higher up. And so we have moved this smallest entry over to the left. So A has moved leftward and no longer appears in beta k or higher. Okay, and so we're going to use these identities, whatever identity is the right one, based on this, to replace beta k minus 1 to beta k, moving A to the left. Okay, and then once we do that, we're now going to repeat this same process, but now rather than looking at everything, just looking at beta 1 through beta k minus 1. And so the important thing to note is that the A ended up here. So A ended up here, and everything to the right in all the other beta k up to beta r, all these entries here are bigger than A. Okay. So what's happening in this process is that we're taking some small numbered entry on the right and we're moving it to the left. And we're guaranteeing that up until the spot that we've moved it, nothing to the right of it is smaller than it. Okay, so A is always going to be, if you're reading it from the right, A is going to be the smallest one that you've read so far. Okay, so I claim we continue this process all the way through, and that eventually, in doing this, eventually we have to get to the situation where the identical 2 cycle is next to itself. And those cancel themselves off, and we've gotten rid of two cycles. Okay. So why can we be sure this has to happen somewhere? Well, let's suppose that it doesn't. So if it doesn't, we keep running through the situation all the way through, then we're going to be able to get whatever ends up playing the role of A at the end. So this is the smallest entry of all the entries in all the 2 cycles, will be by itself in the leftmost 2 cycle, and then everything that appears to the right of it will be bigger than A prime. Okay, so I claim this gives us a contradiction, because now if we applied A prime onto this permutation, you're going to end up with B1, because A prime can't appear anywhere else, right? It is strictly less than all of the other BIs. And so the only one of these 2 cycles that affects A prime is the first one. And so A prime gets sent to B1, and B1 is not equal to A prime. So A prime is not fixed. Not fixed by the permutation, and so that means that this can't actually equal the identity, because the identity fixes all of the elements. Okay, so this is impossible, so we can't possibly get down to this, so somewhere along the way we must have had two cycles cancel themselves off, right? And then since we had to have 2 cancel themselves off, then we had to end up with 2 less 2 cycles in the product than we started off with. Okay, so now using that lemma, now we can prove that any representation of epsilon as a product of 2 cycles is going to use an even number of 2 cycles. And so the proof is, let's do this also by contradiction. Let's suppose that the number of 2 cycles used is odd. Well, then we can apply the lemma m times, and every time that we apply the lemma, we're subtracting off 2 of the 2 cycles. So applying the lemma m times, we're eventually going to end up with epsilon is equal to a 2 cycle. And that's not possible because 2 cycles are not the identity. And so this gives us a contradiction, and so R cannot be odd, so it must be even. Okay, so the corollary, which really to some degree is the most important result in this video, but it's a corollary because the proof is very quick once we have our theorem on how to represent the identity, is that let's take some permutation Sn and break sigma up into 2 cycles, and let's suppose we do it in 2 different ways. So we have 2 different decompositions of sigma into 2 cycles. Well, then the number of 2 cycles used in each of these permutations, they either both have to be odd or they both have to be even, right? And so what that means is that any time, so let's say that k is odd, that means that any time then that we break sigma up into 2 cycles, it's always going to be an odd number of 2 cycles. Let's say k is even, that means that any time that we break sigma up into 2 cycles, the number of 2 cycles used is always going to be even. Okay, so how can we prove this? Well, first thing to note is that if we're taking our product of 2 cycles and we want to invert it, Well, inverting a product of two cycles just means reversing their order. And this is just the socks and shoes principle. Okay. That each two cycle is its own inverse. And so if we're inverting a product of them, socks and shoes says the inverse of a product is going to be the inverses of the things in the product in opposite order, but everything is its own inverse, and so it's just the two cycles in opposite order. Another way to check this is if you just multiply them together, the beta k's will cancel themselves off first, and then the beta k minus 1s will cancel themselves off, and you keep on going all the way down to, at the end, you have beta 1 times beta 1, and they cancel themselves off. Okay. So, and this line is really going to finish off the proof. Since epsilon is equal to sigma times its inverse, the first sigma, we're going to use the gamma representation. So that's gamma 1 through gamma L. For sigma inverse, we're using the fact that we can represent it as k two cycles, just in opposite order. And so in total, we have L2 cycles plus K2 cycles. So there are L plus K total 2 cycles, and it's equal to the identity. And so this means that L plus K has to be congruent to 0 mod 2. So by the theorem, K plus L has to be even. And so then if K plus L is even, that means that they are congruent to each other mod 2. So they're either both even or both odd. Okay. So this, once we break a permutation down into two cycles, and we can count then the two cycles, that means that if we know that it's even, that means anytime we break it into two cycles, it's going to be even. And so that means that this evenness is sort of an inherent property, or it is an inherent property of the permutation. And so we're then going to call it an even permutation. Now, if sigma, on the other hand, is decomposed into an odd number of two cycles every time, then we're going to say that it is an odd permutation. So what's the importance of this? Well, in the symmetric group, Sn, the subset of even permutations, so even permutations, this includes the identity, and any other permutation that is decomposed into an even number of two cycles, they together are going to form a subgroup of Sn. And this subgroup has a special name. It is called An, and it is called the alternating group on n elements. And it turns out that the size of An is exactly half the size of Sn. So if we look at Sn, half of the permutations are even, half the permutations are odd. The even ones form their own group, and they are called the alternating group. That is all for this video. I will see you again soon.